This video is going to look at representing chemical changes. Up to this point, we've used chemical formulas and from the standpoint of writing the formulas, naming the formulas, doing mathematics associated with chemical formulas. In the current lesson and the remainder of the lessons, we will be using chemical formulas combined to represent chemical change. So chemical equations are really our topic here. Whenever we represent chemical change, we represent them with a shorthand notation that's known as a chemical equation. We represent with symbols and formulas the identities and relative amounts of the reactants and products in a reaction. What this amounts to, as far as what's being said here, is that this is a recipe for certain products. Because just as a recipe tells you how much of something you're going to put into a bowl to mix up to make a cake, or and exactly how to go about the cooking of the cake, times and so forth, the chemical equation will also represent, using some sort of shorthand notation, what you're putting together and how much you're putting together. And there may be some other things associated with the equation also that gives you more information, such as if the reaction is heated, or if there's pressure applied, for instance. So all chemical equations have certain requirements that have to be met. Those requirements include, number one, they have to be properly written from their formulas viewpoint. So before you can do anything else with the chemical equation, the formulas have to be written properly. This is something that some of you are going to have to work hard to achieve. Secondly, the law of conservation of mass has to be followed, meaning that matter can neither be created nor destroyed. So every atom that is present at the beginning of a chemical change has to be accounted for at the end of the chemical change. And the way we do that is by balancing. Most of you probably did some balancing in physical science. And again, sometimes chemical formulas also contain other symbols, such as state symbols are important. State symbols include things like G is gas, L is liquid, S, sometimes C, is solid, AQ is aqueous. Some other symbols include this symbol, which is equals to heat, amp is electric current, catalyst or enzyme represents just that, something that's going to speed up a chemical reaction, and there are others as well, but those are just a few common ones. So let's take a look at writing a chemical equation from scratch and going through the process of balancing. First, we've got barium chloride reacts with silver nitrate to produce silver chloride and barium nitrate. Okay, we always have in chemical equations, we have something known as reactants and products. Reactants are the beginning materials, the ingredients that go into the change. Products are the end result. We connect those with the symbol, a arrow pointing in the direction from reactants to products, and this symbol is called yield. So this is red reactants, yield products. When we have more than one reactant, we also connect them with plus signs. So we could have reactant plus reactant yields product plus product. And we would say in this case that substance number one reacts with substance number two to produce or to yield product number one and product number two. So in this reaction, barium chloride reacts with silver nitrate. Okay? Putting that into shorthand, we would write the formula for barium chloride, BaCl2, reacts with silver nitrate, to produce, so that's the to produce is the yield symbol, silver chloride and barium nitrate. Notice in this that I have two nitrates on this side and only one nitrate on this side, nitrate being the polyatomic ion. The reason for that is that I wrote barium nitrate according to barium being a positive 2, nitrate being a negative 1, so we would have a 2 here and a 1 there. So all of the formulas are written according to their oxidation numbers. We don't bring over, because I've got two chlorides here, I don't bring over a 2 to this side. Chloride here is a negative 1, silver is a positive 1, so it's going to be a 1-to-1 ratio. Now, when we look at this, though, we have some discrepancies. For instance, if we used to start with barium, count, we have 1 barium on the reactant side. This is the reactant side. And we have 1 barium on the product side. So we would say that barium is balanced. We look at chlorine, we have 2 chlorines here, only 1 on this side. Chlorine is not balanced, so that's a good place to start, the first thing that you find unbalanced. To balance, we can only put coefficients, or we can only put coefficients, and the coefficient is going to go in front of the formula. So if I want to balance chlorine, I need 2 of them on both sides. I'm going to give myself 2 chlorines on this side. I can't put a 2 out here simply because that changes the formula, and we can't change the formula. So 2 chlorides, but by putting the 2 as a coefficient, that also provides 2 silvers. So I then let that be the next thing that I balanced. I balanced the chloride by putting in a 2. That affected silver and gave me 2 silvers. So I come over here and I give myself 2 silvers. That 2Ag, that 2 silvers, also affects the nitrogen and oxygen. I have nitrate in the reactants and I have nitrate in the products. When you have the polyatomic ion on both sides, it's easier to just say I have 2 nitrates and I have 2 nitrates over here. Notice the 2 ways to get 2. A coefficient of 2 times 1 is 2, and I've got a coefficient of 1 here understood. 1 times 2 is 2. So if you go back and check, 1 barium, 2 chlorines, 2 chlorines, 2 silvers, 2 silvers, 2 nitrates, 2 nitrates. So this is balanced. Every atom is accounted for. So to read this, we would say that for every 1 quantity, that would actually be moles, for every 1 mole of barium chloride, we need 2 moles of silver nitrate to react completely with it. We're going to produce, for every 1 mole of barium chloride and 2 moles of silver nitrate, we're going to produce 2 moles of silver chloride and 1 mole of barium nitrate. Let's try another. Our next example, we're going to have phosphoric acid. Phosphoric acid is going to, let me get a new pen color. Phosphoric acid is neutralized by the addition of sodium hydroxide. So, interpreting this, we would say phosphoric acid, H3PO4, is neutralized by. This is another way of saying reacts with. That's a plus. The addition of sodium hydroxide, NaOH. The reaction products, so they produce sodium phosphate and water. Okay. To balance this, we look for the first item that is not actually balanced. So let's start with sodium. Okay, and there's no necessarily a good reason to start there, but I'm going to start with that because it jumps out that I have 3 and 1. So I'm going to start by putting a 3 here, 3 in front of sodium. That gives me 3 sodium, 3 sodium. Okay, that gives me a total of 3 plus 3 hydrogens. Notice that I've got hydrogen in 2 places. So that's 3 hydrogens plus 3 hydrogens. That gives 6 hydrogens on this side. Over here I've only got 2 hydrogens. So I'm going to put a 3 here. Okay? That gives me 3 oxygens plus 4 oxygens would be 7 oxygens. And on this side I've got 3 oxygens plus 4 oxygens is 7 oxygens. So that's balanced. And then we have phosphorus, 1 phosphorus, and 1 phosphorus. So accounting for everything again, total hydrogen. Hydrogen is in 2 places. 3 hydrogen is 6 hydrogens. 3 times 2 is 6 hydrogens. 1 phosphorus, 4 oxygens plus 3 more oxygens right here is 7 oxygens. I've got 4 and 3 is 7 oxygens. Balanced. Sodium hydrogen carbonate, NaHCO3, reacts with sulfuric acid to produce water, carbon dioxide, and sodium sulfate. So let's begin by balancing sodium. We've got 1 sodium versus 2, so I'm going to give myself 2 sodiums. That 2 affects the hydrogen, so let's check on hydrogen and see where we stand. That gives 2 hydrogen plus 2 hydrogen is 4 hydrogen. I've got all my hydrogen in water on this side, so 2 times 2 is 4 hydrogens. I've got 2 carbons. I've got 1 carbon. Get myself 2 carbons there. And I've got 6 oxygens plus 4 is 10 oxygens. So over here I've got 2 oxygens plus 4 oxygens plus 4 oxygens. 4 plus 4 plus 2 is 10. So we may be balanced. We haven't checked sulfur yet. We've got sulfur here, 1 of them, 1 sulfur over here. This is a balanced equation. Next problem, aluminum reacts with hydrochloric acid and yields aluminum chloride and hydrogen gas. Certain elements are diatomic. You need to know these. These include hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are all diatomic. Whenever you write them in their pure state, not combined with something else like HCl, but when they're in their pure state, hydrogen gas, for instance, the 2 will come after it. They have to be written as diatomic. Otherwise, that's a bad formula. So let's start with looking at aluminum. Aluminum is balanced. Hydrogen, we've got 2 here and 2 here. Looking ahead a little bit, I can see I've got 3 chlorines and only 1 chlorine. So if I put a 2 here, that's going to give me 2 hydrogens and take care of hydrogens, but that gives me 2 chlorines and 3 chlorines, and there's no way I can balance at that point. So what I'm going to look for in this case is I've got to have something that will give me a common multiple between 3 and 2 with this HCl on this side. Let's go with 6. So I'm going to say I need 2 times 3 is 6 chlorine, and 3 times 2 is 6 hydrogen, and I can just put a 6 there, 6 HCl. Now, I did upset the aluminum balance. That gives me 2 aluminum, and I can put a 2 in front of the aluminum without affecting anything else. Balanced equation. All right. From biology, glucose, C6H12O6. Burns in oxygen, burns in, reacts with. Oxygen is one of those diatomic gases. To produce carbon dioxide and water. Okay, first thing off balance is carbon. I've got 6 carbons, 6 carbons. Since I've got oxygen everywhere, I'm going to leave O2 till last, and that way I can put a number in front of the oxygen that's by itself here, and not upset anything else. So I'm going to do hydrogen next. It gives me, I've got 12 hydrogens, 2 hydrogens, so that's 6 times 2 is 12, and then I can check oxygen. On this side I've got 6 plus 2, that's 8 oxygens. Over here I've got 12 plus 6 is 18 oxygens. So what can I do? Well, if I've got 18 here, and let's just look at the 6 here. I'd prefer not to put a number out in front of the carbon because that'll upset the balancing. So if I've got 18 and I take away these 6, that leaves 12 more than I need on this side, and 6 times 2 is 12. Balanced equation. Then we have zinc metal reacting with copper 2 sulfate. Zn plus Cu SO4 yields zinc sulfate and copper. Okay, so I've got, when I look at this, I've got 1 zinc, 1 copper, 1 copper, nothing off balance so far, 1 sulfur, 4 oxygens, 4 oxygens. This equation is balanced as written. So there's nothing saying that if the formulas are written correctly that the equation isn't going to be balanced when you finish. That's a possibility, but always check for it. All right, let's look at another. Aluminum reacts with iodine vapor. This is going to produce aluminum iodide, which is Ali3. Okay, iodine is the only thing off balance here. So I've got 2 iodines and 3 iodines on my 2 sides. There's nothing that I can do to the 2 to make it 3, and there's nothing I can do to the 3 to make it 2. We always have to have simple whole numbers. So in doing this, what I want to do is probably find a common multiple between 2 and 3, which is again is 6. So I can use 3 times 2 is 6, 2 times 3 is 6, and then I've got 2 aluminum, only 1 here, so I give myself 2. And it's balanced. That finishes the introduction to writing and balancing chemical equations. Please make sure that you turn in your notes completely whenever you have finished the video.